For decades, this galaxy did nothing. No flares, no warning signs, no reason to look twice. Then, without exploding, without fading, without dying, it started getting brighter. And it didn't stop. Astronomers watched ultraviolet light rise, then optical, then infrared, month after month, year after year. Supernovae don't behave like this. This wasn't an ending. This was a beginning. Question: what does it look like when a supermassive black hole wakes up while we're watching?
Today we follow galaxy SDSS 1335 plus 0728, quiet for decades, until 2019 when it suddenly brightened across ultraviolet, optical, and infrared light. We'll compare those light signatures to a typical supernova and ask, why hasn't the glow faded? Using observations from ESO's Very Large Telescope and partner observatories, we'll trace the fingerprints of accretion as a 4 million solar mass giant starts feeding again. By the end, you'll know how scientists tell a dormant core from an active galactic nucleus in real time. For years, SDSS 1335 plus 0728 sat in survey catalogs like a quiet entry in a phone book. So why did its light curve start rising and refuse to fold back down the way normal transients do? That single question lit up a lot of dashboards, because steady galaxies don't usually decide to trend. Before the alerts, everything looked routine. Archival checks from wide-field sky maps showed a consistent flux level with small, random wiggles that match instrumental noise and ordinary stellar populations. No standout emission lines that would flag an active nucleus. No flicker that hints at a central engine. It blended into the background of the universe, the kind of target pipeline software catalogs and then forgets. That quiet baseline mattered, because when a change comes, you want to know exactly what normal looked like. Then 2019 arrives, and the alert stream starts pinging. Automated pipelines that sift through nightly images notice a brightening in the ultraviolet, optical, and even the infrared. If you followed typical supernovae, you know the drill. They rise in weeks, peak, and then slide down over a few months as the radioactive core cools. This source did the opposite. It climbed, hesitated, climbed again. Nights turned into months, and the signal kept maturing instead of fading. The first breadcrumb trail came from time domain triggers. Think Zwicky transient facility or a similar watchman, flagging an excess at the galaxy's coordinates. Follow-up photometry from smaller telescopes filled the gaps between survey passes, building a continuous light curve. Each new epoch reinforced the same message: no decline. Observers widened the wavelength net, cross-matching UV archives and tapping infrared monitors to see whether dust was responding. The result was a coherent rise across bands, an odd behavior for a one-off explosion. Lay that curve over supernova templates, and the mismatch gets obvious. A Type I shows a sharp peak and a predictable decline governed by radioactive decay. Type II supernovae have a plateau, then a drop, again on month-long schedules. SDSS 1335 plus 0728 didn't follow those roads. Its luminosity grew over many months and then held, as if something kept feeding energy into the system. That's a hallmark of accretion. Continuous fuel, continuous output. You can test the timescale with a simple yardstick. Supernova decline tracks the half-life of cobalt, 56, which sets a cadence you can almost read off by eye in the photometry. Here, the clock runs slow, with power sustained over years. That kind of endurance points to gas falling inward, not ash cooling outward. Instead of a dying ember, you have a furnace with a fresh supply line. Colors told their own story. The ultraviolet stayed lively, suggesting a hot central source. Optical bands flattened, consistent with a blend of disk light and reprocessed emission. Infrared crept warmer, as nearby dust absorbed shorter wavelengths and re-emitted them at longer ones. That sequence, UV up, optical steadying, IR warming, is what you expect when a buried core lights up and its surroundings start echoing the flare. At that point, the investigation pivoted. Photometry can tease, but spectra decide. Teams put in for spectroscopy on ESO's Very Large Telescope and partner facilities to test the supernova idea against a live spectrum. If the source were a standard explosion, you'd catch specific evolving features and velocities that march through known phases. If a central engine had switched on, you'd expect emerging broad emission from fast gas, plus high-ionization lines that need a fierce UV source. The verdict leaned one way. The data refused the script of a single blast, and instead matched a system still being fed. Brightness persisted. Colors evolved like an engine heating its neighborhood. The evidence lined up with a black hole turning on after a long quiet period. Now the question shifts from not a supernova to how do we prove a dormant core has become an active nucleus? And that answer lives in the fingerprints buried in the spectra waiting on the next page. If a supernova doesn't fit, what tells you a sleeping giant just started feeding while we're watching? The answer hides in the spectrum. When a black hole wakes up, the light doesn't just grow brighter, it grows structured. You start seeing fingerprints that only a hot, energized core can make, and those marks evolve with time in ways a one-off blast cannot sustain. First, let's pin down terms. A dormant nucleus means the central black hole barely sips gas. With little accretion, the core stays dim, and the surrounding gas doesn't get excited enough to glow in special ways. Active is the opposite. Gas piles into a disk, heats to extreme temperatures, and floods the neighborhood with ultraviolet and X-rays. That energy turns nearby gas into a glowing billboard, and it rearranges the infrared from heated dust. You're not just measuring brightness, you're reading a power plant that switched on. There is a competing idea worth testing, a tidal disruption event. That's when a star strays too close, gets torn apart, and a flare lights up for months to a few years. TDEs can look AGN-like at first because they also feed a disk and can launch bright UV emission. The question becomes duration and detail. Does the power fade along a predictable curve, or does it settle into a sustained state with ongoing fuel? Open the spectra, and the story sharpens. Broad Balmer lines, H-alpha and H-beta, appear with widths that imply gas moving at thousands of kilometers per second near the core. High-ionization features show up, such as O3 and He2, which need a strong UV source to exist. The continuum tilts blue in the ultraviolet, consistent with a hot accretion disk rather than aging stars. These aren't generic fireworks. They're signatures of gas bathed in intense radiation from a central engine. Accretion itself works in a straightforward way. Gas loses angular momentum and spirals inward. Gravitational energy turns into heat, and the disk gets so hot that it radiates strongly in UV and optical light. Closer in, temperatures soar, and high-energy photons pour out. Some of that energy drives winds. Some hits surrounding gas, kicking electrons to higher states so they emit those broad lines. The disk is the lamp. Everything around it is the lampshade glowing in response. You can watch the environment respond with a built-in delay. Dust absorbs short wavelength light and re-emits it in the infrared. Because light takes time to travel, the infrared rise lags the UV/optical by weeks to months, depending on the dust distance. Measure that lag, and you get a ruler for the inner dusty region. That reverberation, UV up first, IR following, acts like an echo of the core turning on, a classic response of an active nucleus rather than a single explosion. Sustained behavior seals the case. Over multiple years, the luminosity stays elevated instead of rolling over quickly. Line widths and shapes evolve, hinting at gas flows settling into the gravitational potential of the black hole. Velocities of several thousand kilometers per second place the emitting gas mere light days to light weeks from the center, exactly where an accretion disk and its broadline region reside. A fading TD could mimic parts of this early, but the continued power and stable AGN-like structure argue for a longer switch. Context helps. A black hole of roughly 4 million solar masses sits in the same neighborhood as Sagittarius A* in mass, but here the engine is lit and radiating. That mass scale stakes out the kind of gravitational well needed for those velocities and the disk temperatures that drive the UV excess and high-ionization lines. Put it together, and the checklist lines up: persistent multiband light, broad Balmer emission, strong, O3, and He2, a UV bright continuum, and a dust echo arriving on schedule. That's a dormant core gone active, an accretion disk asserting itself, and a black hole waking into view. Which raises the next question. When galaxies change states this quickly, what does that say about how they build their central engines and reshape their neighborhoods over cosmic time? We're catching galaxy evolution in real time. A quiet core turns on, fuel starts flowing, and the energy budget shifts from starlight to accretion light within a handful of years. That kind of rapid change shows how feedback can heat gas, light up dust, and rewire a galaxy's center on human timescales. If you want more real-time space detective stories, subscribe and tell us which target we should investigate next. Drop your ideas in the comments, and we'll pull the data and follow the clues. The next flare, the next awakening, might already be in the surveys. Keep looking up and keep asking questions.
Thanks for watching. If you enjoyed this journey through the cosmos, hit like, subscribe, and tap the bell. And when you're ready for your next space mystery, click the video right here.